This is question number 6 on chapter 32. A wire of length 1 meter and radius 0.1 mm has a resistance of 100 ohm, and we need to find out the resistivity of the wire. So the way I try to solve problem is to tell you that you don't need to memorize the formula or everything. So it has a length of 1 meter and radius of 0.1 mm. And we have find that this resistance is 100 ohm. The one thing that we need to remember, and we don't need to even remember that, we know that the resistance is directly proportional to the length. So the more length the wire has, the more resistance it offers to the flow of the electron. The resistance is proportional to the length, and resistance is inversely proportional to the area. If you provide more area, then it provides more path to the flow of electrons, and it has less area. And if you remove this proportionality constant, we get a constant, and this constant is called the resistivity, and that's what we need to find it out. Resistivity, rho will be equal to R into A divided by L. R is given 100 ohm, area is going to be pi R square. R square is 0.1 into 10 to the power minus 3 whole square divided by 1 meter. So this is 10 to the power minus 4 squared becomes 10 to the power minus 8 multiplied by 10 to the power 2, it becomes 10 to the power minus 6. It's pi into 10 to the power minus 6 ohm. In case of resistivity, just make sure you know what it is proportional to, and you don't need to memorize the formula, just follow it logically. Next problem is question number 7. A uniform wire of resistance 100 ohm is melted and recast into a wire of length double that of the original. What would be the resistance of the wire? If you melt it and increase its length, then its length will increase, that will increase its resistance, and it's obviously because the volume is same, it will become smaller in cross-section area, and the smaller cross-section area means less room for the electrons to flow and more resistance. So that is, we are guessing that its resistance will be higher. We initially had a length L, keep it L, and then let's say initially it has a resistance of R1. It says that its length is doubled. So now we have a length of 2n. Let's say initially it has an area of R1 and the new radius of R1, the new radius is R2. Now the material stays same, so for in this case the resistance R1 is given by rho L upon pi R square. So, and in this case the resistance R2 will be given by rho into, the length has been doubled, 2L divided by pi into R2 square. Rho is the resistivity of the material. If we divide these two equations, we will keep this on the top and this in the bottom. So R2 divided by R1 will become equal to rho cancels out. So 2L divided by L is 2, and this becomes 1 upon R2 square divided by 1 upon R1 square. So R1 square divided by R2 square. If we know this ratio, R1 square by R2 square, we are done. And for this, we'll get this ratio. We know that the same material is melted and extended. So our volume stays same. The volume in this case is pi R1 square area multiplied by the length. And that becomes equal to pi R2 square, the new radius, multiplied by this new length 2L. So length has increased. To compensate is the R2 will become lower, and we will know that from here we get R1 square divided by R2 square is 2. If you L cancels, bring R2 here, R1 square pi cancels, R1 square divided by R2 square is equal to 2. So this R1 square by R2 square is 2. If we substitute it here, we will get R2 divided by R1 is equal to 2 into 2 or R2 is equal to 4 into R1. R1 is 100 ohm, so R2 is equal to 400 ohm. So you can do similar problem when volume is kept constant, it's melted, turned into some other shape or something like that.